Hello everyone. Today we are going to look at section 3.3 and section 3.4. So starting with section 3.3, we're going to be talking about data description still. We're still on chapter 3, so we're still talking about data description. And section 3 is on measures of position. So we've talked about measures of center and measures of variance, or variation rather. The measures of center were the mean, median, and mode. Measures of variation were the range and the variance and the standard deviation. And now we're going to talk about measures of position. And some of the measures of position that we're going to talk about from the learning objectives here: identify the position of data, of a data value in a data set using measures of position such as percentiles, deciles, and quartiles. Okay, so those are the three that they list here. And out of those, I just want to mention that the quartiles is actually going to be probably the one we talk about the most, because we also have a graph that we're going to learn how to do that utilizes the quartiles. The graph is called a box plot. Okay, so let's move on to our first thing that we're going to talk about with measures of position. So if you recall from the last section, we talked about Chebyshev's theorem. We talked about measures of position already, kind of, because we were talking about what a standard deviation was. So if we think about measures of position, and again, I'm going to put some numbers in here because I think it's easier for folks to grasp when you see some actual numbers. So when we're talking about z-scores, we're just simply talking about the number of standard deviations away from the mean. Okay, so the z-score, they also call it here the standard score, but that's really not used very often in the rest of the book. So if we look at, say, a mean, if we give a mean of, say, let's do something really easy. Let's say 30. And then let's say actually let me make that 40. And then let's say that our standard deviation is 3. That means that in the center of our data, we have x bar, which in this case is 40. And then if we go up to 43, then that would be s, that would be plus 1s, and that would be 43. So we're saying what we're measuring in are 3's because our standard deviation is 3. So it's kind of like if you're measuring in feet, every 12 inches is a foot. So you're measuring in sections of 12 inches. Or if you're measuring in yards, you're measuring in sections of 3 feet. So in this case, we're measuring how many s's away we are, and the size of an s is 3. So in this case, by going up 1 standard deviation, we're going up by 3. So then, of course, if we go to 2 standard deviations, then we're at 46, because again, we're going up by 3 each time, which is the s. Then if we go up to 3 standard deviations, we're at 49, and we'll go up 1 more. And the data can go past that, but as we learned from Chebyshev's rule, most of the data is within 4 standard deviations. So then this would be 52. So we have plus 1, plus 2, plus 3, standard deviations plus 4 standard deviations gives us 43, 46, 49, 52. Now if we go the other direction, if we go 1 back, then that is at 37. If we go back 2 standard deviations, we're at 34. If we go back 3 standard deviations, then we're at 31. And if we go back 4 standard deviations, then we're at 28. Okay, again, every time we make a move this way, we're doing minus 3. Because again, 3 is a standard deviation. So if, say this is scores on a test that had 55 points on it. Okay, the average score on the test, according to this, and we're looking at a sample of the exam because this is, I'm using X bar and S. So we took a sample and the average of the sample was 40. If someone scored a 46, then we could say that student scored 2 standard deviations above average. So we could say that in 2 different ways. We could say what they actually scored, or we could say it's 2 standard deviations above the mean. So a score of 46 is the same in this situation as 2 standard deviations above the mean. And so if you relate that to what a z-score is, that means that the z-score is 2. So for somebody who scored a 46, their z-score is 2. So it's a simplified name for how many standard deviations you are above the mean. So in this case, 2 standard deviations above the mean gives you a z-score of 2. So how does that fit with our formula? So the formula is, if we have x minus x bar, then in our case, the x would be the 46 that we were looking at. The x bar would be the 40. And then the s would be the 3. So remember, we got 2 when we did it on our number line here. So let's look at it without the number line. Let's do it with the formula. 46 minus 40 is 6. 3 is what we divide by, and we get 2. So this is a way to, without drawing the number line, calculate the z-score. So in this case, 46 minus 40 gives us 6. That's divisible by 3 twice, because that's the, adding 6 is the same as adding 3 2 times. And we're measuring in 3s because our standard deviation is 3. So you're measuring from whatever the mean is, and then you're measuring how many of those s's you have gone up or down. Now remember, if someone scores below average in this case, then you're going to get a negative number. So let's say somebody scored a 37. Okay, let's use a different color. Let's use black. Okay, so let's say somebody scored 37, and we can see on the number line that that's 1 standard deviation below average. So let's use the formula. The formula would say, take 37, that's our x, subtract the average, which is 40, the mean, divide by 3. Well, the top now gives us negative 3. Divide that by 3, and we get negative 1. So the z-score for that person that scored 37 is negative 1, because they were 1 standard deviation below average. So you might be thinking to yourself, well, what do you do if somebody's not right on one of those? Well, you get a partial z-score, like you get a fractional part to your z-score. So let's pick another one. Let's say that someone scores, let me grab a different color here. And let's say that somebody scores so we want to go in between 2 values. So let's say somebody scored a 45. So that doesn't fall on 43 or 46. You know, here's 43, here's 46. It's in between those. So let's say that their score was a 45. Okay, so they score, their X is 45. Their score, whatever that student scored, was a 45. Then you would take 45 minus 40 and divide by 3, which gives us 5 divided by 3, which gives you 1.7 if you round that. It would come out to be 1.6 repeating, and then we would round that to 1.7. Okay, so we've already done some examples, kind of did a little bit above and beyond what we needed to do at this very point, but I wanted you to understand what these z-scores are, because otherwise it just feels like you're playing some game that you don't know the rules or the purpose to. So this is what we're trying to determine, and it's a way that you can take, say, different tests and say, well, this student did better in comparison to their classmates than this student did in a different test in a different class. But if you compare their z-scores, even if the test didn't have the same number of points or the same average or the same S, you could still compare them by comparing their z-score. So let's look at their examples. Okay, so in this case, it says, suppose the mean height of a 3-year-old child is 38 inches with a standard deviation of 0.7. So for now, you won't have to do this every time, but for now, I'm going to go ahead and make our number line so we can visualize what we're talking about here. Okay, so through the magic of pausing, I have our number line here. So let's start to fill in the information. So it says that our average is 38 inches, and so we're going to put that on our number line in the center, and that is our X bar. Make this a little bigger. And then we're going to add 0.7 as we go up this way, and we're going to subtract 0.7 as we go this way. So plus 0.7 and minus 0.7. So 38 plus 0.7 would be 38.7. And then the next one would be 39.4. And then the next one would be 40.1, and then we'd have 40.8. Okay, again, each time adding 0.7, and then this would be 1 standard deviation, 2 standard deviations, 3 standard deviations, 4 standard deviations. So we can see that if a child had a height of, say, 39, that they would be between 1 and 2 standard deviations if they were at 39. So now let's go in the other direction, and if we subtract 0.7, we have 37.3, and if we subtract another 0.7, we have 36.6. And then if we subtract another 0.7, we'll be at 35.9. And then if we subtract another 0.7, we'll be at 35.2. Okay, so we'll mark this. This is minus 1 standard deviation, minus 2 standard deviations, minus 3 standard deviations, minus 4 standard deviations. Again, we shouldn't need any more than that for our number line, because most values, according to Chebyshev's theorem, are 94% are going to fall between negative 4 standard deviations and 4 standard deviations. Okay, so now they give us some actual values. It says, suppose a 3-year-old child is 40 inches. So what is that going to be? That's going to be our X. Okay, the 38 is our X bar. And the 0.7 is going to be our S. And then it says Okay, so we have other information here for an 8-year-old child, but we're just going to stick with the 3-year-old child for now. Okay, so the 3-year-old child, and I know you can see it right here, but I'm just going to work it out. In order to get that z-score, you're going to take x minus x bar, and then you're going to divide by s. So for the 3-year-old, their x was 40. Their x bar, I'm sorry, yeah, their x was 40, their x bar was 38, and then their s is 0.7. So in this case, the child was 2 inches above average. Divide that by 0.7, and you get that they're at the 2.9 z-score. If we go up to here, you can see that right here. So here's 2. 2 would have been 39.4, and they're even a little bit above that. So they're between 39.4 and 40.1. So they're just a little bit below 40.1 at 40. And so they're at 2.9 standard deviations above average. 40.1 would have been 3 standard deviations. Okay, so now we're going to use that and we're going to compare that to their sibling, but their sibling has completely different information. So if we look at the sibling, I'm not going to do the whole number line out for the sibling, but their number line would have a, let me get rid of some of this mess up here. Okay, so each sibling is going to have a different information depending on their age. So for an 8-year-old, the mean is 51. So that would have been our number here in the middle, would have been 51 for the 8-year-old, and a standard deviation of 1.3. In other words, 8-year-olds vary more in height than 3-year-olds do. Which, if you kind of think about things, 3-year-olds have a more typical height than 8-year-olds. As children, get older, the variations in their heights gets greater between children. Okay, so if we measure this, now this 8-year-old, it says, and their 8-year-old sibling is 53 inches. So for this case, the 51 was our x bar, the 1.3 is our s, and for this sibling, the x is 53. So x minus x bar, in this case, divided by s, is 51 inches. Sorry, 53 inches for the x. The x bar is 51. And then we divide that by 1.3, because for 8-year-olds, the standard deviation is 1.3. So in this case, the sibling was still 2 inches above average, but if you divide that by 1.3, you only get 1.5 when you round it. It doesn't come out to be exactly 1.5. It rounds to 1.5. So which child, according to their peers, has a relative higher difference in their height? And the answer is the 3-year-old. So the 3-year-old is taller relative to the other children their age than the 8-year-old is. So it's more unusual, we could say, for a 3-year-old to be 2 inches above average than it is for an 8-year-old to be 2 inches above average. They're still both above average. They still both have positive z-scores, but relative to their peers, the 3-year-old being 2 inches higher than the average is less common than being an 8-year-old and being 2 inches above average. And so, as I said, this gives us a way to compare things when the averages aren't the same, and especially when the standard deviations aren't the same between two groups. In this case, the groups are, differences in heights, but it could be any sort of data that you collect. And so I thought it would be interesting, this wasn't actually in the original slides, but I thought it would be interesting to look at a slide of average in this case it's weights, with the standard deviations marked. So this is from the WHO, the World Health Organization. This is how most growth charts used to be marked. They've actually changed them now where a lot of them have like the 75th percentile and the 95th percentile or something like that marked. But they almost used to always be marked with standard deviations. So in this case, this black line represents 3 standard deviations above average. The red line is 2 standard deviations above average. And then the same down here, we've got -2 standard deviations and -3 standard deviations. They don't mark 1, I think, just because it gets kind of messy or clustered when they do that. But if you notice, as we mentioned, when a child is younger, they tend to be closer together in their height, or in this case, their weight. But as they get older, so in this case, let me move this so we can make sure you can see it. It goes from birth to 5 years old. So babies versus 1-year-olds versus 2-year-olds, they have a closer, you know, from the center up to here, or the center down to here, is not as wide of a gap as it is for when you get up into the 4-year-olds and the 5-year-olds. You can see that the gap from there for the 5-year-olds, or close to the 5-year-olds, I don't want to make this too messy, but from 0 up to 3 or down to 3 is a lot bigger for the 5-year-olds than it is for the 2-year-olds. Okay, so so the question asks, what does the z-score of 0 represent? So what does this right here, this 0, this green 0 in the middle, what does that represent? What does that line, or that curve rather, represent? Well, that represents the mean. Okay, so this is the mean weight of the girls. Okay, so if you follow this green line, if you look at, say, a 2-year-old, let's look at a 1-year-old because it's easier to read. So if we look at the 1-year-old, here is what's considered the mean, and if we follow that over, that is between 8 and 9 kilograms, right at about 9 kilograms. Okay, so a 1-year-old mean weight would be 9 kilograms. At birth, it looks like the mean weight is about 3 kilograms. And you could do that for all the ages. Let's see, 2 years old, we will go ahead and do it. It's not right in between 10 and 12, though. It's closer to 12, so it's probably like 11 and a half for a 2-year-old, 11 and a half kilograms. Okay, so you could do that for any of those. So the one that we're going to look at, though, we're not going to look at the average. We're going to look at the z-score for a child that's not at average. So let's say you have a 4-year-old who weighs 13 kilograms. Then you're going to look here until you find 13 kilograms, and then you're going to follow that over until you get to the 4-year-old. Okay, so we're going to keep going, keep going. And then we're going to mark that up from the 4-year-old. Okay, it looks like we've got everything lined up. And so we can see that that is not quite -2. Okay, it's not quite on the red, but it is close to the red. So we can't get an exact value here, but it looks like it's a little bit past halfway. So I would say maybe -1.5 for the z-score. And we can't get an exact value off of the chart. All we can do is approximate from the chart. But that gives us a general idea. You know, we could do that for different values. Let's say you had a 3-year-old that fell right here. Then we could say that they are Okay, so that would be 18 kilograms. So if you had a 3-year-old that was at 18 kilograms, then you would say, oh, they're 2 standard deviations above average. Okay, so just kind of interesting to see that this is used in actual science type data so that you could see how this would be utilized. Okay, so let's go down and look at our next measurement that we're going to talk about, which is percentiles. Oh, I did want to show you one thing. Let me pause for just a second and show you this one thing that's on your formula sheet that you get to use on the exam. So here's the formula sheet that you're allowed to use on the exam. And I just wanted to point out that even though we're doing this in Chapter 3, it does not show this formula in Chapter 3. So there will be a question like this on the exam, but notice that the formula for this is under Chapter 6. So even though we're starting to talk about it in Chapter 3, on the formula sheet, it does not show this formula until Chapter 6. So please remember that when you're taking your exam, that you can look over here. You may not even need it because it's a simple enough formula that you just might remember it for the exam, but there will absolutely be a question on the exam of computing the z-score within Chapter 3. I always keep the test in order, so it'll have a heading of Chapter 3. So under the Chapter 3 section on the exam, there will be a question of, here's some values, compute the z-score. Okay? And so the formula is over in Chapter 6, because in Chapter 6 we come back and talk about z-score, and we talk about it a lot in Chapter 6. I wish they'd put it over in Chapter 3 too, but they don't. So in Chapter 3 also, but they don't. Okay, so let's get back to to the next measurement that we're going to talk about here, which are percentiles. So percentiles are a position measured a lot of times in education and in health-related fields. So if you'll notice, if you've ever gotten your test scores back, your standardized test scores, which we'll talk about what standardizing is, what does standard mean, but a percentile is often given as one of the measurements for your test scores when you take your standardized test in school. So for example, the STAR tests or the Iowa Test of Basic Skills, or even like your SAT or ACT scores. And those are often given to you as a percentile. So it will say something like you were at the 65th percentile. Well, what does that mean? Well, that means that you scored better if you took a sample of 100 students. On average, you scored better than, say this is the 50th percentile, this is the 100th percentile. Say if we took a sample of 100 students, you would have scored better than 65 of those students. So that means you're at the 65th percentile. So in an average sample of 100 students on this exam, which was given to thousands and thousands and thousands of students typically, you scored, out of an average 100 students, you scored better than 65 of them. That's what the percentile means. And so the reason it's called a percentile is because percent means per 100. Okay, literally means per 100. So a percentile means out of 100, where would you fall? So it divides the data set into 100 equal groups. The smallest data value is the P0, so the very lowest score, and then the largest data value would be the P100. And anything in between, again, it would depend on what group of students fell within that range of data. Okay, so I wanted to show that same chart. Remember I said that sometimes they give these same charts with percentiles. In fact, this is more common now, which makes my mathematician's heart a little bit sad because I think the Z-scores are a little better information. But what does a weight at the 50th percentile represent? Well, in this case, the 50th percentile was a 0 z-score. It means it's the mean. So this is the same data that we had on the other chart. It's just that what is marked here is the 50th percentile instead of a 0 for the z-score. So the 50th percentile, this green line here, is the mean weight at all those ages. And then approximately what percentile would a 4-year-old who weighs 13 kilograms be at? So the same measurement we were having before, 13 kilograms for a 4-year-old. Let's look at that with this chart. So 13 kilograms, we're going to come all the way over. Oops, I'm at the wrong mark. Hold on a second. I'm at 11 kilograms. I was like, that's looking very low for a 4-year-old. Okay, let me get on the right spot. 13 kilograms. So if we bring the 13 kilograms all the way over to 4 years old, which is here. Again, we want to line it up with 4 years. And we can see here that that is between the 3rd and the 15th percentile. Looks like it's a little bit closer to the 3rd percentile. So we would just have to, again, kind of make an average. It looks, I'm going to say, looks a little bit closer to the 3rd percentile than the 15th percentile. So I'm going to say maybe the 8th percentile. And so this child, in this case, is measuring quite a bit under average. If you took 100 children, that child would only be taller than 8 of the 100 children. Again, if you measure, compare that to our z-score, a z-score of negative 1.5 is quite a bit below the average. Negative 3 standard deviations below average would be very considerably low, and they're at about negative 1.5. Okay, so z-scores versus percentiles, and we get the respective comparison values there. Okay, so now let's look at how we compute, if we have some data, how do you compute the percentile rank? So the percentile rank is computed by taking the number of values below x, okay, so you have to count how many values are below it, adding a half, and then dividing by the total number of values. And then we multiply it by 100 to get it to be a percentile, because it's per 100. And so if we look at this data set, and again, they were nice enough to put it in order for us. If it wasn't in order, we'd have to put it in order. So they've already given us the data array with the numbers in order. And it says we want to find the percentile rank of 13. Okay, so we want to know what's the percentile rank for 13. So the first thing that we have to do is we have to count how many values are below 13. So there's 1, 2, 3, 4 values. There's 4 values below 13. So that's going to be our first number that we put in the formula. So the percentile rank for 13 would be 4 plus 0.5 and then divide by the total number of values. So there was 4 and now we have 5, 6, 7, 8 total values. So out of the 8 total values, 4 of them are below 13, and then there are 8 total. And so we're going to compute 4.5 divided by 8, and then multiply that by 100. So 4.5 divided by 8 would give us approximately 5625. In fact, I think it comes out to be exactly 5625. Then multiply that by 100 to switch it to a percentage, and you get 56.25 percentile rank. And then with percentiles, we usually don't take it to a decimal place. And so typically what would be done here is you just say you're at the 56th percentile instead of the 56.25 percentile. So percentiles are almost always rounded to the nearest percentile. So 56.25 rounds to 56. Now, this seems kind of strange when we're talking about only 8 pieces of data. As I mentioned before, what this really works better for is for really large data sets. So it would be much better if we had thousands of scores, or at least hundreds of scores, but definitely more than 100 or more. When you have a small data set, taking a small data set and then comparing that to 100 seems a little strange. But if you have hundreds or thousands and you want to kind of bring it down to a more readable or understandable level, comparing it to, well, what would that compare to as 100 makes a lot more sense. But for the sake of being able to do this work, we've got this small data set. And that's the exact same thing that they would do with the large data set. They do that same computation. Okay, now we can also go in the other direction. So if we wanted to figure out, if we wanted to have a percentile and figure out what data set or data number in the set corresponded to that, the formula is C equals N times P over 100. So the N is the number of values in the data set. And then the P is the percentile rank that you're trying to find. And then divide by 100. Since before we multiply by 100 and we're going backwards, then we're going to divide by 100. And then the C is the number, it's the count, okay? So this is the C'th number in the set, which seems, again, a little strange, but I'll show you what that means here when we get to one. Also, as far as your index cards that you're building, we really want to include N. And so N is the number in the data set. We're going to use that all through the rest of the book, so that would be a great thing to add to your index cards. Okay, so a couple rules. If we get a C that's not a whole number, we just round up to the next whole number. And then that percentile will be the C'th number in the data set. If the number C is a whole number, then we go in between that number and the next number. And we're going to do an example of each here. And just kind of for your knowledge, I probably won't ask a percentile problem on the test. In fact, I won't ask a percentile question on the test. There are some on your homework, but it's not going to be a test question. There definitely will be a question regarding z-score, but there won't be one on percentile. So you'll have some chance to practice it in the homework, but it's not, in my opinion, not important enough to put on the exam, and I can't put everything on the exam. Okay, so let's say we have this data set again, and let's say we wanted to find the 80th percentile. So using that formula, remember it's C equals N times P over 100. So the N in this case is how many there are in the data set. So 1, 2, 3, 4, 5, 6, 7, 8, remember. Then we're going to multiply it by the percentile, which in this case is 80. And then we're going to divide by 100. And that gives us 6.4. So we're going to look at and then if it doesn't come as a whole number, remember we're supposed to round it up. So this rounds up to the 7th number in the set. So we're going to count 1, 2, 3, 4, 5, 6, 7th number in the set is 21. So 21 is the 80th percentile. Okay, so now let's do one for a C that falls as a whole number. So same calculation. In this case, we want the 25th percentile. So we still have 8 values in our data set. And then we're going to multiply that by 25. So our n is 8, our p is 25, and then we're going to divide by 100. And that comes out to be exactly 2. So we don't go up here and say, okay, 1, 2, it's 7. When it falls right on a whole number, you have to go between that one and the next one. So between 7 and 11 is what we're going to calculate. We're going to figure out what's right in the middle of that. So we're going to average 7 plus 11 and divide it by 2, which comes out to be 9. So a score of 9 would be at the 25th percentile. Okay. So we got an example of each. If you get confused on your homework, you can always come back and look at these 2 examples. All right, so the last thing that we're going to talk about before we talk about those quartiles that I kind of mentioned are going to be one of the most important things are deciles. We're not going to talk a lot about deciles. Deciles are exactly like percentiles. It just breaks it into 10 instead of into 100. So if you're looking at a set of data, if you knew what the 10th percentile is, that would be the first decile, because decile is every 10%. If you knew what the 20th percentile was, that would be the second decile, and so forth. And that's really about all we're going to talk about with deciles. Okay, so now we're going to talk about quartiles. So with quartiles, we are now, instead of breaking the data into 100 pieces or into 10 pieces, we're breaking it into 4 equal pieces. So quartiles divide into 4 equal pieces, which makes a lot of sense why this is called quartiles. I mean, percent means per 100, per 100. Decile is based off of the prefix deca, which is 10. And now we have quartiles, which quart is like a quarter. Okay, so quart means 4, quarter means a fourth, and so that's where the terms come from. So we've actually already done something that is a lot like quartiles when we have done the median. So if you think about, just to kind of give a silly example, but I think it's helpful. Whoops, hold on a second. Let me put a decent shape in here. Okay, so if you had a circle, if you had a pizza, let's say, and you wanted to cut that pizza in half, okay, that's typical to, or that would be comparable to the median. But if you then wanted to split the pizza into 4 pieces, then if you split each half in half, so if I split this half in half and I split this half in half, now I have 4 pieces. So this is kind of a circular version of what quartiles do. So what we're going to do is we're going to, so this would be like the first piece, the second piece, the third piece, and the fourth piece if you're going around the pizza. Okay, so instead of doing that, we're going to be finding the median, and then we're going to be looking at the median of the data, and then we're going to be looking at each half of the data in order to calculate where the quarters are on either side. So the first quartile always matches up with the 25th percentile because it's 1/4 of the data. They usually do it in percentiles, but you can also think of it as 1/4. The second quartile, we actually don't usually call the second quartile. It's the 50th percentile, but that's the median. And so that's where 1/2 of the data lies up to the second quartile. So Q2 is the same thing as the median. So we usually call it the median. And then we have the the third quartile is the 75th percentile, and there you typically have 3/4 of the data below that. And then if you want to calculate the inner quartile range, this will make more sense, I think, when we do the box plot that I mentioned. But the inner quartile range is how far it is between the first and the third quartile. So it's Q3 minus Q1. And within that, because that's between the 25th and the 75th percentile, then you're going to have 50% of the data. So 75 minus 25, it's 50% of the data. Something I always like to relate this to is, and I'll say it again when we get to the graph, is if you think about like a sports event that has 4 quarters, like a football game, so, or a basketball game. Each quarter is 25% of the game, time-wise. So if we thought about, you know, the game, and you said, okay, we're going to have the start of the game here, and then after 1 quarter, we'll call that the end of the first quarter. And then after the next quarter, we could call that Q2. We could call it the end of the second quarter, but we can also call it halftime. Okay, so that matches up or kind of meshes with the median. So we have a special name for that halftime. So this is like at the beginning of the game, after quarter 1, after quarter 2, but we could also call the end of quarter 2 halftime. And then when we get to the end of the third quarter, we could call that Q3. And then when we get to the end of the game, we could call that the end, or the maximum. So what we're going to call this when we get to the graph, we're going to call 0 like the minimum and the end like the maximum. Instead of 0, let me put start. Okay, so you have the start of the game, you have the end of the game, and then you have it split into 4 parts. So time-wise, half of the game occurs before halftime, half of the game after, a quarter of the game in quarter 1, a quarter of the game in quarter 2, a quarter of the game, so 1/4 or 25% of the game is before the end of the first quarter, 25% of the game is between the end of the first quarter and end of the second quarter, or before halftime, and then 25% of the game is between halftime and the end of the third quarter, and then another 25% of the game is between the end of the third quarter and the end of the game. So kind of keep that in mind when we're looking at this data, if that helps you visualize it a little bit better. So let's look at these examples. So I'm going to rewrite this off to the side. I know again that it's here, but I want to show it fresh. So let's put our numbers up here, and you'll have a chance to see where this is coming from without it just marked up. All right, so we have 9 values here. So 1, 2, 3, 4, 5, 6, 7, 8, 9 values. Okay. Okay, and we want to break this up into quartiles. So the first step when you're breaking into quartiles is to first, like the pizza, cut it in half. Okay, so we're going to find the median. Okay, so if we look at the median, that would be the 76. That gives us 4 values to the right and 4 values to the left. So 64, 69, 71, and 74 are below 76. And then 78, 83, 89, 195 are above 76. Now what we do is we look at each half and we cut that into half. So on the left, we have 4 values, so we have to go in between the 69 and the 70. And then on the other side, we have to go between the 83 and the 89. So we average them. 69 plus 71 divided by 2 gets us 70. And if you can see that, I mean, this one's kind of fairly easy because they're only 2 apart. So obviously the average between 69 and 71 is the number right in the middle, 70. But if you can't see it, you can compute it. Okay, this one's a little bit harder to see. So if we take 83 plus 89 and we average those, that comes out to be 172, which then averages to 86. So 172 divided by 2, and we get 86. So what does that mean? Well, that means that the Q2, or better known as the median, is 76. That means that the Q1 is 70, and that means that the Q3 is 86. So a quarter of the data falls below the Q1. A quarter of the data falls between 71 or 70 and 76. A quarter of the data falls between 76 and 86. And then the final quarter falls past 86. So each of these is roughly 1/4 of the data. Again, this works better, honestly, when you have really big data sets, but we don't want to work with really big data sets because that would be very time consuming. So we've got to use these small data sets, but this works and makes more sense when you have big data sets. Okay, so the interquartile range is the difference between the Q3 and the Q1. So in this case, instead of looking at all of the quarters, we could say, well, 50% of the data, roughly 50% of the data, is between 70 and 86. And so the interquartile range is the Q3 minus the Q1, which in this case is our 86 minus our 70, which means our interquartile range comes out to be 16. All right. And we'll have another example of that because we're going to do it when we do the graph that I spoke about. Now, the last thing that we're going to talk about in 3.3 are outliers. So outliers we've talked about briefly, I think, but outliers are either extremely high values or extremely low values. And those extremely high or low values can cause your data to be skewed. It can also bring up your average, your mean. And so outliers are oftentimes important. Measures of center variation and position can be strongly affected by outliers, especially the mean and the standard deviation. Those ones that are significantly affected are called non-resistant statistics. Again, not something I'm going to ask you on the exam, but that's what they call them. They call them non-resistant, so they're not resistant to the effects of an outlier. So mean and standard deviation are non-resistant. Other measures, such as the median or the interquartile range, are not as affected by the outliers, because remember, the median is just the middle. So if you have a really high value, that still doesn't change where the middle of the data is. Or if you have a really low value, that still doesn't change where the middle of the data is. But it could bring down the mean because that is from adding them all up. So the median and the interquartile range are what's considered resistant statistics because they aren't as affected. And where do outliers come from? Well, it could be from error on the part of the researchers, like they did a measurement error, a recording error, they got a sample that wasn't representative of the population, or it could just be from chance because things, unlikely things still happen. So when you're talking about, say, people's income, you do have people that have extremely high incomes. You have people that have extremely low incomes. Now, if you take a relatively small sample, are you going to find one of those people? Not necessarily. But if you do, that could become an outlier. So let's look at how we detect an outlier? How do you tell if something is an outlier? Well, it's kind of a judgment call, honestly. There's no hard, fast rule for it. Statisticians will disagree on what the formula is for computing an outlier. But one of the more common ones are to check for a lower outlier to take the Q1 minus 1.5 times the interquartile range, and to look for an upper outlier to do Q3 plus 1.5 times the interquartile range. And that's what our book uses. So that's what you can use on your homework. So our data from before, we had 64, 69, and so on, up to 195. And we found that the Q1 was 30, the Q3 was 86, and the interquartile range was 16. So let's calculate what a lower quartile would be. So we want to compute Q1 minus 1.5 times the IQR. So Q1 was 70, that's what we computed before, minus 1.5, and then the interquartile range that we found was 16. Yeah, I'm going to go up here and just point out where I'm getting these from. So this is just from the data that we had before. Remember, we found the Q1 to be 70, the Q3 to be 86, and then we found the interquartile range to be 16, the 86 minus the 70. So those are the numbers that we're using. And if we put that in and calculate that out, that's 70 minus 1.5 times 16 would be 24, and then that comes out to be 46. So what we're going to do is we're going to look at our data and we're going to say, is there anything below 46? And the answer is no, because the lowest is 64. Okay, so our lowest was 64, so there's nothing that's below 46. So there's no lower outliers. But then we have to do the same thing for the other side. So let's look at the calculation for Q3 plus 1.5 times the IQR. IQR is going to be the same. IQR is going to be 16. And our Q3 was found to be 86. So we're going to put 86 in there. And so 86 minus 24, because 1.5 times 16 is 24, that comes out to be 62. So now we want to know, since this is the upper, is there anything above I made a mistake. Hold on. I was like, something is wrong here. I'm not supposed to be subtracting. I'm supposed to be adding on this side. Okay, so that's 110. So is there anything above 110? And the answer is yes. Now I have 83. That's fine. I have 89. That's fine. But whoa, I also have a 195. So yes, we do have something that's above 110. And you probably noticed it when we were looking at the data. You're like, oh, these are pretty consistent until we jump from 89 up to 195. That's a pretty big jump. And it is. So 195 is considered an outlier. So that is considered an upper outlier. And if we were looking at this data, if this last value had been just 100, that wouldn't have changed where the median was. It wouldn't have changed what the interquartile range was, but it sure would affect the average if we calculate, the arithmetic average. If we added these all up and divided by 9, that 195 would be a really high value. I don't think they gave us a scenario for this, did they? No. Oh, yes, they did. This was the resting heart rates for 9 people. Okay, so if we look at these, you have most people in the data set that are, 64 to 89 for the resting heart rates, and then you have this one person that's all the way up at 195. That's a heck of a resting heart rate. So they're considered an outlier, and that would probably be considered by their doctor to be a concern, depending on the situation. So an outlier is something that's far above or far below what is the other typical values in the data set. Okay, so now we're going to finish up by learning how to do this box plot. Box plots are based entirely off of the quartiles. So we're going to kind of be continuing our discussion of quartiles. And it's just a visual representation of the quartiles. So we're on section 3.4. We're still talking about data description, and now we're talking about something called exploratory data analysis. So it says we're going to use the techniques of exploratory data analysis, including box plots and 5-number summaries, which sounds like two different things, but the 5-number summary is what we use to get the box plots, and that's our objectives for this section. Okay, so in the 5-number summary, sounds like a big important name, but the 5-number summary is just what we did with the quartiles. Okay, so exploratory data analysis is a method for examining the data to see what can be discovered about where its center is, what its spread is, and the 5-number summary is often used. Well, the 5-number summary is just the things that we calculate to get the quartiles, the Q1, the median, and the Q3, and then we just add to that the minimum value and the maximum value. That's the 5-number summary. It's not anything super magical. So if we take the 5-number summary, we can make a box plot. A box plot is what it's typically called now. When I was in college, we called them box and whisker plots. And if you look at this picture down here, you can see the reason it's called a box and whisker plot is because it has a box in the middle and then it has these little whiskers on the side, like some little cute animal with whiskers. Okay, but now they tend to just call it a box plot. And it's a way to visually represent the 5-number summary, which includes the quartiles. So to draw a box plot, you're going to draw a number line that spans from the minimum value down to the maximum value. So I'm going to point that out as we talk through it. So from the minimum to the maximum. You got to make sure that your number line down here at the bottom goes at least from the minimum to the maximum. It doesn't actually have to go any further past that, as long as it goes from the min to the max. Then you're going to place a point above the number line at the minimum and at the maximum. Above the number line, you're going to draw a vertical line segment at the median, at the, hold on, having a failure here. Okay, at the median, at the Q1, and at the Q3. So you make those 3 vertical marks. How big do those have to be? It doesn't matter. They can be real short, they can be real tall. You'll see box plots where those vertical lines are really wide, and you'll see ones where they're super skinny. There's no standard for that at all. So just whatever you're comfortable with. And then we're going to connect the tops of the vertical segments from Q1 to Q3 and on the top and the bottom. And then we're going to draw these whiskers in on each side. Okay, so this box plot had a 5-number summary of 12. You see right here, that was 12. So that was the minimum value. The largest value was 24. The median was 19. That's why we have that mark right there in the middle of the box. And then, so this is the median. And then 15 was the Q1. And 22 was the Q3. And then it gives us an idea. And this one is pretty evenly spread. You could see that the whiskers and the 2 pieces of the box are pretty similar in size. So this was pretty evenly distributed data. Okay, so let's look at constructing a box plot. So we're going to start from scratch and we're going to construct a box plot. Again, I know the answers are here, but if we draw this out and do it together, it'll make a lot more sense where it came from. Okay, so here are our values. We have to list them in order so that we can get the median and the quartiles. Okay, so we're going to start by finding the median, because again, just like cutting a piece of pizza, you don't cut it into 4 separate fourths. You find the middle, and then you cut each of the halves in half again. So we're going to cut it in half. This happens to have 10 data values, so half would be between 43 and 45. That gives us 5 below and 5 above. And so if we want to find that, we're going to average those. Again, this one's easy to see, but if it's not, you can go through the process of adding and dividing by 2 to get the average. So in this case, the median is at 44. Then we're going to go to each half and find the middle of that. So on the left, 43 is in the middle, and on the right, 48 is in the middle. So this is the Q1, and this is the Q3. Now you've noticed this is kind of opposite of what we did when we did our first quartiles. Before, our middle was right in the middle, and so that one was just circled, and each half we had to average. This time, our median we had to average, and then our halves were right in the middle. It just depends on how many there are. You could have a data set where they're all averages. You could have a data set where they all fall right in the middle, and you don't have to do any averages. So, in relation to what we're doing, it could be all circles, all bar averages, or it could be a mix of both of them. Okay, so we've got our Q3, our Q1, our median, and then I like to use just an underline for the minimum and maximum. So the minimum is 41, the maximum is 51. So if we're going to write out the 5-number summary, we have minimum of 41, Q1 of 43, median of 44, Q3 of 48, and then a maximum of 50. So now if we're going to make our box plot, we're going to make our number line along the bottom. Okay, so we make our number line, and then we're going to make sure that we go from at least 41 to 50. Okay, so you can start below 40 if you want to, or 41 if you want to, but you don't have to. Okay, so we've got 41, 42, 43, 44, 45, 46, 7, 48, 49, and 50. Okay, so then we're going to, as we said on that other one, we're going to first put a dot here and here. Okay, so the minimum and the maximum are going to get dots at them. So we're going to have a dot above 41, and we're going to have a dot above 50. Then we're going to put bars at each of the quartiles. So we're going to put a bar at 43. We're going to put a bar at 44. We're going to put a bar at 48. And then we're going to connect the top of the bars. So connect the tops of all the bars to make our box. And then we're going to make our whiskers. So we connect our box out to our biggest point. Sometimes you'll see these points as like little marks instead of actual dots. Like they'll make it, I'll do it on this one. So they'll make it like this instead of an actual circle on each end. They'll put like a little mark, but our book tends to use the dots. So I just do that to follow along with what our book does. Okay, so that's your box plot. And if you wanted to mark, you could mark, you know, this is the minimum, max. This is the Q1. This is the median, and this is the Q3. So what does that mean for our data? Well, for our data, you can either look at theirs, there's one here, and then there's ours. But if you look at these, you can tell that the center of the box is more to the left. So our center on this one is more to the left. This is a much smaller box here than here. So we've got a smaller box between Q1 and the median than we do between the median and the Q3. Well, what that indicates is that because it's to the left of center, then the distribution is actually skewed right. In other words, there's data that kind of drags out to the right, and so that pulls up the mean away from where the median is. So this data that's more spread out to the right, so it's more spread this way, that means that the data would be skewed to the right, whereas to the left, it is more compact. So the data to the left is more compact, whereas the data to the right is more spread out or skewed to the right. And so you can look at the graph and fairly quickly recognize the pattern of the data. And researchers, especially when they use these graphs a lot, are really good at looking at it and being able to interpret it fairly quickly. So now we're going to do one last thing on interpreting a box plot, and then we'll be done with chapter 3. In a box plot, remember that each bit is a quarter of the data. So I've marked that on this one real clearly. So from the median down to the minimum, remember that that is the lower 50% from the median to the minimum. Mark this. So from minimum to the median, that's 50% of the data. Okay. Then when you go from the median to the maximum, that's another 50% of the data. And then in each piece, you've got 25% of the data. So 25% of the data is between the minimum and the Q1. 25% of the data is between the Q3 and the max. And I didn't mark this, so let me mark it in here. There's also 25% of the data in each of the boxes. So 50% between the Q1 and the Q3, that's the IQR. I'll put that here too. So that's the IQR. But there's also 25% of the data here and 25% of the data here. So there's 25 in each of the pieces, each whisker and each portion of the box. So for our box plot, if we look at that, that means that where is 25% of the data? Well, 25% of the data, or the first 25% of the data, falls below, here's Q1, here's our median, here's our Q3, here's our min, and here's our max. Okay, so we know that 25% of the data falls between the minimum and the Q1. So when it says 25% of the data falls below blank, well, 25% of the data falls below the first quartile, so below 43. But remember that everything has to add up to 100%. So if 25% of the data is below 43%, that means that 75% of the data is above 43%. So you could ask that in either direction. You could say above what value is 75% of the data? Well, that would be 43 also, because there's 25%, 25%, and then 25% in the last whisker. Okay, so let me get rid of these marks so that we can look at the next question. So now we've got 25% of the data falls above what? Well, each of these is 25%, and we want the top 25%. Where's that at? Well, that would be above 48. So 25% of the data falls above 48. So 25% of it is here. But that means that 75% of it is below that, because together that has to be 100%, because that's all of the data. So you could say 25% falls above the 48, or you could say 75% falls below 48. Now the 50% I think is a little easier to understand, because that's right at the median. So if we look at 50% of the data, the median is right here. Okay, so you've got 50% below, and you have 50% above. So 50% below, 50% above. I think I said that backwards than what I wrote. Okay, so 50% below, 50% above. So 50% falls below the 44, which is the median, and 50% falls above the 44, which is the median. And then we could also say that between 43 and 48 is 50% of the data, because each of these boxes is 25%. So from Q1 to Q3 would be 50% of the data, which is also, again, the IQR. So the IQR is from 43 to 48. In this case, and so 48 minus 43, the IQR is 5, and so between those two values where you find the IQR of 5, that's 50% of the data. And that's all we have for Chapter 3. Best of luck on your homework. Let me know if you have any questions, and have a great rest of your day.